Okay, in this lecture we're going to start our Chapter 2 material on vectors and in general vectors in space. And in section 2.1 we're going to start by introducing vectors in two dimensions, or vectors in the plane. So let's start by defining a vector. So the definition is as follows. A vector is a quantity such as a velocity or a force that has both magnitude and direction. So in particular, when we talk about forces or think about forces, forces have some magnitude, like the strength of the force, but they also have a direction. We need to know in a lot of physical problems what direction a force is being applied in. Or in the case of velocities, well, if we're talking about how rapidly something is moving, we would call that quantity speed. But if we're also interested in the direction in which an object is moving, that's known as velocity. It's both speed, how fast an object is moving, and direction, in what direction that object is moving. So these are pretty classic examples of vectors. Now, when we think about defining a vector in a mathematical context, we will define a two-dimensional vector as an ordered pair of real numbers. So let me talk a little bit about notation here. So in this course, when we're looking at vectors, vectors will be denoted by some variable in boldface. And it's an ordered pair of real numbers. So it's similar to the notation that we would use for a point in the plane. But for vectors, instead of parentheses, we use these little angled brackets around these values A1 and A2. And the numbers A1 and A2 are called the components of the vector A. Now, when we write a vector by hand, so in the notes or in your textbook, you'll notice that all vectors are written using boldface. However, we can't really write in boldface by hand. So the notation that we'll use for vectors when we're writing them by hand would be to use a variable a, and then we're going to put a little arrow over it. So this notation is what we would use by hand to denote a vector A, which has components A1 and A2 that we would write in these angled brackets. So let's think about what our components represent and how we might be able to visualize vectors in the plane. So we can define what's called a representation of a vector as an arrow that has an initial point and a terminal point, where the length of the arrow represents the magnitude of the vector. So if we're talking about velocity, it would represent speed or how fast our object is moving. Or if we're talking about force, it would represent the magnitude or the strength of our force. That's the length of the arrow. And the arrow will point in the direction of the vector. So the direction that this arrow points will indicate the direction in which our object is moving, if we're talking about velocity, or the direction in which some force is being applied, if we're talking about a force. So geometrically here, a vector, let's call it A, would be represented as an arrow that has some starting point, which we call an initial point, and a final point, which we call a terminal point. So what do the components of a vector represent? Well, the components, A1 and A2, indicate how much this vector is acting in the positive x and y directions of the plane, respectively. So for the representation that we have for our vector A here, the direction that we're moving horizontally from the initial point to the terminal point is the component A1, and the direction that we're moving vertically from the initial point to the terminal point is A2. So these are what the two components of a vector represent, is how much this vector is acting in the horizontal or vertical directions. Now, there is a special representation of a vector, which is given a particular name. So a vector whose initial point is at the origin is called a position vector. So let's think about representations of vectors. We'll take a look at what it would mean for two representations to be equivalent, or what exactly this position vector represents. So let's say that we're looking at vectors in the plane, so in 2 dimensions, using a Cartesian coordinate system. We have the xy plane, and a representation of a vector would be some arrow with an initial point and a terminal point. Let's call this vector maybe v for vector. Now I can draw another representation of this same vector at a different initial and terminal point, and I would say that this representation is the same as the first representation I had drawn, or these two different representations are of the same vector v, as long as the length of my vector is the same, and as long as these two representations are parallel to one another, or in other words, as long as they're pointing in the exact same direction and have the exact same length, then they are representing the same vector. So I can draw a representation of a vector v anywhere I want in the plane, as long as I have the correct length and the correct direction. And the specific representation of v, where I choose my initial point to be the origin, is called a position vector. So when we talk about a representation of the position vector, or the position vector corresponding to a vector, we are referring to the representation whose initial point is at the origin. But as I've explained here in the figure that I've drawn, all of these representations are of the same vector v, since they all have the same direction and the same length. Now, a problem of interest that will come up frequently throughout this course is determining the components of a vector with a given initial and terminal point. So we have a theorem which tells us how to find a vector between 2 points. And here's what it says. If we're given the points A, which has coordinates x1, y1, and B, which has coordinates x2, y2, then the vector whose representation is the vector from point A to point B is denoted as follows. So we would say AB with a little arrow above it. So that is used to denote the vector whose initial point is A and whose terminal point is B. And the components of this vector are given by x2 minus x1 and y2 minus y1. So that is the difference between the coordinates of the terminal point, x2, y2, and the coordinates of the initial point, x1, y1. And let's think about why this theorem makes sense. So if we have in the plane some point A, whose coordinates are x1, y1, and we have some other point B, whose coordinates are x2, y2, then the vector whose representation is from A to B would have a horizontal component given by the horizontal distance that we traveled. So that is the length of this x interval, which would be given by the difference in the x coordinates of my 2 points. And the second component of this vector would be the vertical distance which I traveled from the initial point to the terminal point, which would be given by the difference in the y coordinates of those 2 points. So this vector is denoted as AB with a little arrow above it. So let's look at an example of finding a vector with given points. So here we are asked to find the vector which is represented by the directed line segment, or the arrow, with initial point 4, -1, and terminal point 1, 2. And then we are asked to draw the vector AB and its corresponding position vector. So let's start by finding the components of this vector, whose representation is the arrow from point A to point B. So we said that the first component, or the x component of this vector, would be found by taking the difference in the x values. We take the terminal point where x was 1, and then we subtract the initial x value, which was 4. And our y component would be found by taking the difference in the y coordinates for these 2 points. So the y coordinate for the terminal point was 2. We're subtracting the y coordinate from the initial point, which was -1. So simplifying a little bit, the vector that we're describing is the vector whose components are -3, +3. Now, we're also asked to draw the vector AB and its corresponding position vector. So let's get a set of axes here. So here, the initial point of our vector was 4, -1. So we have our point A here. And then our terminal point was the point 1, 2. So our terminal point B shown here. So a representation of this vector AB is the vector, or the arrow, that moves from point A to point B. Now, we're also asked to draw the corresponding position vector. So that would be the vector whose initial point is at the origin. So I'm going to start at the origin, and let's think about how to find the terminal point of this representation. So the vector AB had components -3, +3. So that means that this vector will act 3 units in the negative x direction, or will move from its initial point 3 units to the left. So since our initial point is the origin, we're moving 1, 2, 3 units to the left. And then the y component of my vector was +3, which means from my initial point, I'm also moving 3 units upward. So the terminal point, if I start at the origin, would be the point -3, +3. So I can see here that this is a representation of the same vector. So they have the same length and the same direction. However, one has its initial point at the origin, so that is what we call the position vector. Okay. Now, another problem of interest that will show up a lot over the course is determining the magnitude or the length of a vector. So let's define how to find the magnitude or length of a vector. So here the magnitude, or sometimes we say length, of a vector A, whose components are A1, A2, is denoted as follows. So we write the vector A inside of this sort of a double absolute value. So that's known as the norm or the magnitude of a vector. And it's given by the square root of the sum of the squares of the components of our vector. So we take the first component of A squared plus the second component squared and take the square root of that value. And of course that sort of makes sense from a geometric interpretation. So if we have some vector A and its components are A1 and A2, that is the horizontal and vertical distance that we travel from initial point to terminal point, then we can see here we have a right triangle, and the length of the vector, or the length of this arrow, which represents this, we denote as the magnitude of A, or the length of A. And from the Pythagorean theorem, it would be the square root of the sum of the squares of the legs of this triangle. That is the square root of A1 squared plus A2 squared. Now there's only one vector that has zero magnitude or zero length. So the only vector that has length 0 is called the zero vector, and it's denoted by boldface 0, or by hand we would say a 0 with a little arrow over it. And the components of this vector are both 0. So this is the only vector that has no specific direction either. Since its components are both 0, it does not act in any specific direction. So this one particular vector that has no length or no direction is called the zero vector. Now the next thing we're going to look at before we jump into some more examples will be some arithmetic or vector algebra. So anytime we introduce a new object in mathematics, like functions, vectors, numbers, we ask ourselves, well, what are some operations that we can perform on those objects? Can we add, subtract, multiply, divide these things? So let's start talking about some operations on vectors. I'm going to refer to this theorem as some vector algebra. And in this theorem, let's suppose that A is a vector whose components are A1, A2, and B is a vector with components B1, B2. And let's suppose that C is some scalar, which is really just a real number. So when we start talking about vectors, we will refer to real numbers as scalars sometimes. So the first operation that we'll talk about for vectors is called scalar multiplication. So we ask, well, can we take a vector A and multiply by a scalar or a real number C? And yes, we can. So it's denoted as C times A. And this vector is found by taking the components of A, which were A1 and A2, and we're multiplying each of those components by this scalar C. So scalar multiplication is found by taking the components of a vector and multiplying each of those components by the given scalar. So let's think about what scalar multiplication represents geometrically. So geometrically, we would say that scalar multiplication is represented by scaling the magnitude of A, or the length of A, and or reversing its direction. So let's think about what different scalar multiples of A would represent. So let's suppose that we have a vector A whose representation is something like this. So if we take a scalar multiple of A, let's say C times A, where C is some constant greater than 1, perhaps 2, for instance, that would then increase the magnitude or the length of my vector. So for instance, if I were taking 2 times A, I would have the vector that is acting in the same direction as A, but has twice the length. Or if I took 10 times A, I would have a vector that is 10 times the length of A, but it would act in the same direction as A. Now, if I were to look at a scalar multiple of A where my constant C is between 0 and 1, like let's say maybe 1/2 of A, well, that would shorten the length of my vector. So I would have a vector that's acting in the same direction as A, but has a different magnitude or different length, depending on what constant I multiplied by. Now, if we take a constant multiple of A, or scalar multiple of A, where our constant C is some negative number, let's say if C is negative, then I would be reversing the direction in which my vector acts. So if I multiply the coefficients x and y by a negative, I'm then reversing the initial and terminal points of my vector. So I would get the vector that's acting in the opposite direction of A. And of course, if we were taking a number like C equals -2, well, that would both reverse the direction of A. So maybe this first one I drew might be a representation of -A. Or if I take a constant like -2 and multiply by A, well, that would correspond to reversing the direction of A and scaling its length by a factor of 2. So these scalar multiples of vectors are vectors which either act in the same or the exact opposite direction of a given vector and have possibly different lengths. So let's look at another operation. Another operation we could discuss is vector addition. So can you add two vectors? Yes, as long as they're vectors in the same space. So for instance, two vectors in the plane, A and B, can be added, and the vector A plus B is found by adding the components of the vectors A and B. So our first component would be the sum of A1 and B1. And our second component would be the sum of the second components of A and B, that is A2 plus B2. Now geometrically, how can we define vector addition, or how can we represent vector addition? Well, it's represented by using either the triangle or the parallelogram laws. So let's suppose that we have two vectors whose representations are given. So let's say A, and then we have another vector B. So if I want to add A and B, I can think about the representation or the sum of these either using the parallelogram law or the triangle law. So let's look at each one of these. So to make use of the triangle law, we're going to take the first vector in our sum, which was A. We're going to take its representation. And at the terminal point of A, I'm going to take the other vector in my sum, that is vector B, and draw its representation, where the initial point of B will correspond to the terminal point of A. So the sum of those two vectors here would be the vector that completes the triangle. So here we would have A plus B as the sum, and this is referred to as the triangle law. So again, to use the triangle law, you place the initial point of one of the vectors at the terminal point of the other vector, and then the vector A plus B is the vector which completes that triangle. Now an alternative approach here would be the parallelogram law. So we could take the vector A, or its representation, and at the initial point of A, I'm also going to place the initial point of my vector B and draw its representation. So the sum of A and B would be the vector that spans from the same initial point of A and B across the parallelogram that would be defined by these vectors. So if I think about copying B as a representation up here and copying A as a representation across the vector B, then I have this parallelogram, and the sum A plus B has the same initial point as A and B, and it is the vector which moves from that initial point across the diagonal of that parallelogram. And that is referred to as the parallelogram law. So either approach we can use, we see that we would get the same representation of that sum. So let us consider then vector subtraction. So the vector A minus B is defined as follows. It would be the vector whose first component would be the difference in A1 minus B1, so the difference of the components of A and B. And the second component would be A2 minus B2, the difference in the components of the second components of A and B. So geometrically, how can we think about vector subtraction? Well, let's consider a representation of it below. So really, the way that we can think about vector subtraction is in the following way. We're taking a vector A and subtracting B, we can really think of as adding the negative, a scalar multiple, that is -1 times B. So let's think about what our representation would be. So using the same vectors that I did for vector addition, let's suppose that we have a vector A whose representation is shown here, and we have a vector B whose representation is shown there. So when we take negative B, we would get the vector that has the same length as B, but is acting in the exact opposite direction. We just reverse the direction of the vector B. And the difference, A minus B, can be thought of as the sum of A with negative B, which I can visualize that sum then using the triangle or the parallelogram law. So let me use the triangle law to illustrate here. So I would take the representation of A, and at the terminal point of that representation, I'm going to draw the representation of negative B. So then the sum of those, A plus negative B, would be the vector that completes that triangle. So it moves from the initial point of the first vector to the terminal point of the second. So I would have A plus negative B, which is what we define as A minus B. So now that we've talked about different operations that we can perform on vectors, such as scalar multiplication, addition, subtraction, or how to find the length or magnitude of a vector, let's look at some examples of this. So in this next example, we're given two vectors, A, which has components 2, -1, and B, which has components 6, 7. And we're asked to find, in part A, the magnitude of the vector A. So recall that the magnitude, or the length, of the vector A would be found by taking the square root of the sum of the squares of its components. So that is the square root of the first component, 2 squared, plus the second component, which was -1 squared. So altogether we have root 5 as the length or the magnitude of A. Now in part B, we're asked to calculate the sum of A and B. So recall, to get the sum of two vectors, A and B, we just add their components. So the first component of this sum would be found by taking the sum of the first components of A and B, 2 and 6. And the second component would be found by taking the sum of the second components, -1 plus 7. So we have 8, 6 as the sum of A and B. Now for A minus B, we have the vector whose components are the difference of the components of A and B. So for our first component, we would have 2 minus 6. And for the second component, -1 minus 7. So we then have the vector -4, -8 for A minus B. And in part D, we're asked to calculate 3A plus 4B. So in order to do this, let's first calculate the vector 3 times A. So to get 3 times A, I'm going to take the vector A and multiply each component by 3. So my first component, 2 times 3, would be 6. And the second component, -1 times 3, is -3. And then we're adding the scalar multiple 4 times B, where B was 6, 7. So taking 4 times those components, well, 6 times 4 is 24. 4 times 6 is 24, and then 4 times 7 is 28. So then taking the sum of those two vectors, I have 6 plus 24, which is 30, and -3 plus 28, which is 25. So we now know how to perform some operations on vectors, and we have a way to represent these operations, a way to visualize what we're doing. So the next thing we're going to talk about is determining a unit vector associated with the given vector. So let's start by introducing some terminology. So we would say that a unit vector is any vector that has a magnitude or a length of 1. Now, if we have any non-zero vector, so we have, let's say, some vector A, which is non-zero, so it has some positive magnitude and some direction, then we can find the unit vector, that is the vector of magnitude 1, that has the same direction as A, as follows. So we would call this vector U, maybe for unit vector, and it's found by taking the vector A that we're given, and I would multiply by the scalar 1 over its magnitude. So if my vector had length 3, I would multiply that vector by a scalar 1/3 in order to shrink its length or its magnitude down to 1. Or sometimes this is denoted as a fraction, A divided by the magnitude of A. All right. So visually here, if I have some vector A, which is non-zero, so it does have some positive length and an indicated direction, then a unit vector acting in the same direction as A would be this vector u, where the magnitude of u is equal to 1. And this is found by taking the vector a and dividing by the magnitude of a. All right. So let's look at an example of this. In our next problem, we're asked to find the unit vector that has the same direction as a, which is given as 3, -5. So in order to do this, I need to find the magnitude of that vector. So let me start by finding the magnitude, or the length of a, which would be given by the square root of the sum of the squares of the components. So that is the square root of 3 squared plus -5 squared. So that gives me the square root of 9 plus 25, which is root 34. So now, in order to find a unit vector, that is a vector of length 1, that points in the same direction as a, well, I would take u as the vector a divided by its magnitude. So I would have 1 over the magnitude, which was root 34, times the vector a, which was given as 3, -5. And to get this scalar multiple of that vector, well, I would just take each component and multiply by the scalar. So I get 3 over root 34, -5 over root 34. And this would be my unit vector of interest. Now we can ask other problems like this that are somewhat similar. Let's say that I wanted a vector that had length 7 and acted in the same direction as a. So in order to get that, well, what I found was a unit vector in the direction of a, which is what I was calling u. So this points in the direction of a and it has length 1. So to get a vector of length 7, I would then just take 7 times u. Or we could ask the question, let's say I want a vector of length 5 that acts in the direction opposite of the vector a. So I know that my unit vector that I found u has length 1 and points in the exact same direction as a. So to reverse the length, I could take the negative of u, and then to get a vector of length 5, I would multiply that negative of u by 5. So we can get other associated vectors of a given length and acting in the same direction as a vector or the exact opposite direction. All right, and that's a problem that will come up repeatedly throughout the course. So another bit of terminology, or another way that we can denote vectors, is by using a standard basis vector representation. So let's define a couple of special vectors in the plane as follows. So we would say the unit vectors, which are vectors of length 1, denoted by I, which would be the vector 1, 0, and j, which is the vector 0, 1. These are vectors whose representations point in the directions of the positive x and y axes respectively. And so these are what are called the standard basis vectors. So to visualize them, if we're working in the xy plane, the vector I, which was 1, 0, is the unit vector, or vector of length 1, which acts in the positive x direction. We move from the origin 1 unit to the right and 0 units upward or downward. And the vector j, which is 0, 1, would have its initial point at the origin. We move 0 units to the left or right and 1 unit upward. So these are called the standard basis vectors. And what's special about these vectors is that any vector A whose components are a1, a2 in the plane, can be expressed in terms of the standard basis vectors. So in particular, A would be given as a1 times the vector I, which was 1, 0, plus a2, our second component, times the vector j, which was 0, 1. And of course, we can verify that by thinking about how these things are defined. We would have a1 times I, which is 1, 0, plus a2 times j, which is 0, 1. So we have, for this first scalar product, a1, 0, plus for the second one, we have 0, a2, and so taking the sum, we have a1, a2. So any vector in 2 dimensions can be written in terms of these standard basis vectors. So we'll use both notations throughout the course. We will denote vectors A either using the angled bracket notation, like a1, a2, or we will use the notation a1 times the standard vector I plus a2 times the standard vector j. So just be aware that both of those notations will be used in the course, so just be familiar with the fact that those are equivalent notations of the same vector. Now the next thing we'll talk about is an alternative way to think about representing vectors, making use of what we talked about from polar coordinates. So often we will represent or describe some vector in terms of its magnitude and the direction in which it acts in terms of an angle measured from the positive x-axis. So let's introduce this. Suppose that we have a vector A whose components are x, y, which has magnitude or length r, and it forms an angle theta measured counterclockwise from the positive x-axis. So let's suppose here that we have in the plane some vector. I'll draw its position vector representation so that its initial point is at the origin. So this is my vector A. And let's say that the magnitude or the length of that vector is r. So the length along this line segment is r. And let's say that this vector forms an angle when measured from the positive x-axis counterclockwise is theta radians. So what are the components of this vector? We were calling our components here x and y. Well, geometrically, x is the horizontal distance I travel from the origin outward, and y would be the distance traveled vertically from that initial point to that terminal point. And this is a right triangle. So from what we know about polar coordinates, the vector A, whose components are x and y, could be described in terms of the polar coordinates, where x is equal to r cosine of theta and y is equal to r sine of theta. So we now have a way to represent vectors, or find the components of a vector, if we know its magnitude, which we would call r, and the angle theta that it forms from the positive x-axis. There are certain problems which might be posed in this way. We'll see some examples at the end of this section. So let's consider a few examples of this. So in our first example, we're asked to find the components of the vector A, which has a magnitude of 4, so here r is equal to 4, and it forms an angle of 60 degrees measured counterclockwise from the positive x-axis. So let's visualize it first. We have in the xy plane some vector of magnitude 4. I'm going to call this vector, let's call it A. And we were told that it formed an angle of 60 degrees rotating counterclockwise from the positive x-axis. And we want the components of that vector. So we just explained that such a vector A would have an x component given by r cosine theta and a y component given by r sine theta if we're making use of these polar coordinates. So r was 4 and theta was 60 degrees. So we have r cosine of 60 degrees and r, which is 4 sine of 60 degrees. So let's see what we have here. We have 4 times cosine of 60 degrees is 1/2. And then 4 times sine of 60 degrees is √3/2. And so simplifying a little bit, our first component is 2. The second component is 2 times the square root of 3. And that would be our vector A. So we can describe it in terms of that magnitude or angle it forms from the x-axis, or an alternative way to describe it would be using its components, which were 2 and twice the square root of 3. So let's look at another one. In this next example, we are asked to find the components of the vector A, which has a magnitude of 6 and forms an angle of 150 degrees, reading carefully here, measured clockwise from the positive x-axis. So let's visualize this. We have in our xy plane a vector of magnitude 6, and which forms an angle of 150 degrees but measured clockwise from the positive x-axis. So rotating clockwise 150 degrees, we're 30 degrees short of a 180 rotation. And then we're taking a vector whose magnitude is 6. So this is the vector we're calling A. And we want the components of that vector. So here, there's a couple of ways we can find this. One way would be to find the angle that we would rotate through in the counterclockwise direction to produce that same vector. So here we can start by saying the corresponding counterclockwise angle would be found by taking a full rotation, 360 degrees, and subtracting the 150 degrees which we rotated clockwise, leaving us with 210 degrees in the counterclockwise direction. So let me label that here in my figure. So using our formula, we could define A, whose x component would be r, which was 6 here, times cosine of that counterclockwise angle, 210 degrees, and y would be 6 times sine of the 210 degrees. So we have then 6 times negative √3/2, and 6 times sine of 210, which is negative 1/2. So simplifying a little bit, our first component would be negative 3 times the square root of 3, and our second component is negative 3. Okay. Now, another way that we could have gone about finding this would be to do the following. Let's think about maybe a slightly different approach here. So if we are sketching our same vector, magnitude 6, acting in this direction, if we think about the angle that's formed between the x-axis and our vector, we would have a 30-degree angle. So to get that 210-degree rotation in the counterclockwise direction, well, we rotated 180 degrees and then went 30 degrees past that. So we're rotating 30 degrees downward from the x-axis. So making use of some properties of trig functions, we could also have found the components of A in terms of that angle as follows. So I could take the magnitude of my vector, which is 6, and then take cosine of the angle measure 30 degrees from the x-axis, and 6 times sine of 30 degrees, which would be the angle from our x-axis. But now I've got to be a little careful about the signs of these x and y components. So I see from sketching my vector representation that it lies in quadrant 3, or the terminal point lies in quadrant 3, which means that my x and y coordinate, or components of these vectors, will both be negative. So if I put a negative in front of both of these terms, then I get exactly negative 3 root 3 and negative 3, the same value that we found by using that 210-degree angle. So it's a matter of personal preference there, whether you like to use the angle measured from the x-axis upward or downward, and then just consider the sine based off which quadrant you lie in, or whether you prefer to think about the full angle measure as rotated from the positive x-axis. So either approach works. I leave that up to you to decide which method you prefer.